So this is going to be our first lecture of this new unit, Origins. Origins is going to be about all things evolution, and we're going to start by talking about the formation and evolution of the universe, of Earth, and everything that's on Earth. So Origins. Origins of the universe, of Earth, of oceans, and the atmosphere. So the origin of the universe, obviously the best place to start is in the very beginning. How did the universe actually form? Well, the most widely supported theory right now is the Big Bang theory. And essentially this theory is saying that the universe began as a point and it's been expanding ever since. To this day, the universe continues to expand. So the universe was originally packed into a dense sphere of hydrogen about the size of today's sun. That sphere of hydrogen exploded, forming a gigantic expanding cloud. The debris in that cloud, the parts of it began to condense and form billions and billions of galaxies, which we can see when we look up into the nighttime sky. The reason why the Big Bang Theory is so well supported in the scientific community is there's a lot of evidence to support the theory. One source of evidence is redshift. So as stars are moving away, the light appears red. When stars are moving towards us, the light appears blue. So scientists have seen a lot of what we call redshift, a lot of red light indicating that galaxies and stars are moving away from our point in the universe. There's also been a lot of cosmic background radiation that gives sort of a Doppler effect. Doppler effect is the same idea as a redshift, except it's more of sound. Think of like an ambulance or a fire truck. When you hear the siren, as it's moving towards you, the sound waves are actually condensing, or it sounds like they're condensing. And then when the fire truck and the ambulance is moving away from you, those sound waves, they sound like they're actually lengthening. So this background cosmic radiation has some of that same effect. So even as of today, the redshift gives us evidence that galaxies continue to move outward, away from our point in the universe. So this image is an artist's interpretation of what the Big Bang Theory may have looked like and what was actually happening. So as you can see, from the moment that time began, within 1 second there was a lot going on. The cosmos went through a super expanding from the size of an atom to that of a grapefruit, just in a fraction of a second. And then after that inflation, the universe starts to form what we will later identify as electrons, quarks, other particles. The next step is after, obviously this explosion is creating a lot of heat. Once that heat begins to cool, other elements are forming, and actually the elements that are already there also begin to condense, and they start to form things like protons and neutrons. So you can see a lot was happening in a very short amount of time because there was so much energy and so much heat created from this gigantic explosion. Alright, so that's the universe. But what about Earth? How did Earth get here? Well, Earth is in a galaxy. It's in the Milky Way. And the hypothesis that tends to be most supported in the scientific community about Earth's formation is the protoplanet hypothesis. And if you recall, proto means the beginning of something. So protostar is a brand new star. So protoplanet is a brand new planet. So about 5 billion years ago, there was this giant cloud of gas and dust that was rotating in space. Most of the cloud's material gathered in the center, causing it to shrink and rotate faster because that center was so dense and so heavy. It was creating this sort of gravitational pull. The compression of all of those particles and materials coming together at the center, that compression made the interior so hot that hydrogen fusion began and the sun was born. And to this day, the sun continues to produce hydrogen fusion, and that's what we feel as heat here on planet Earth. So masses surrounding the sun collected to become planets. It's a very simplified explanation of the protoplanet hypothesis, but it's really all you need to know for this class. All right, so how old is the Earth? How old do you think the Earth is? It's estimated to be about 4.6 billion years old, so it formed shortly after the sun formed. We believe the sun is about 5 billion years old and that it has about another 5 billion years to live. I shouldn't say live because it's not alive. We think it has about another 5 billion years of existence, so it has about another 5 billion years of hydrogen fusion. Once the sun burns up all of its hydrogen, it will no longer have a fuel source, and it will begin to slowly implode upon itself. And anything that is surrounding the sun, anything that is affected by the gravitational pull of the sun, including planet Earth, will be sort of sucked into that implosion. So what is some evidence that we have for supporting the age of the Earth? Well, some of the oldest rocks on Earth date back to almost 4 billion years ago. Australia, there hasn't been a lot of tectonic plate movement on the continent of Australia itself because there are no tectonic plates that go through the continent of Australia. So Australia is surrounded by a tectonic plate, but there are no tectonic plates that actually go through the continent. So a lot of the crust of Australia has been undisturbed since the formation of the Earth. And there has been some rocks found on Australia that date to about 4.1 and 4.2 billion years old. And also there were some moon rocks found to be approximately 4.6 billion years old. Scientists believe that the moon formed around the same time as the Earth. One hypothesis is that there was this giant explosion at about the same time that the Earth formed, and this giant sort of, I guess you could say asteroid, but it was about the size of Mars, crashes into Earth and it sends all this rock and debris flying up into space, and that rock and debris coalesced to form what we know as the moon now. However, there's been some recent research that shows the Earth is slightly younger than what we think, that the Earth may only be about 3.6 to 3.9 billion years old. However, that research is very preliminary at this point, so we can't say for sure. It still puts us in about roughly the same timeline. All right, so what did early Earth actually look like? So we have the sun that formed because of hydrogen fusion, and the sun is creating this gravitational pull, and the gravitational pull causes all of the rocks and debris that are around the sun to coalesce into planets. But what did planet Earth look like when it was a protoplanet, when it was a new planet? Well, early Earth was uninhabitable for life as we know it. It was basically just this big hot bowl of molten lava that was a uniform mix of minerals and elements. So everything was just kind of equally mixed up in this protoplanet. However, over time, Earth began to cool. As Earth began to cool, magma differentiated. What does that word differentiated mean? What it means is that heavy elements sink towards the center. So elements like iron, which are very heavy, sink towards the center of the Earth, and lighter elements accumulated towards the top. Lighter elements like silica. Silica is what sand is made out of. So what happened is 3 distinct layers of Earth formed. We have the hot radioactive core that's made out of that heavy iron, the molten mantle, which is considered liquid, but don't think of it as liquid like water. Think of it as liquid like cake frosting or maybe peanut butter, probably a little bit thicker than peanut butter. And then on top of that molten mantle, that liquid molten mantle, is floating this thin, brittle crust. And the crust is what we walk on every day. So differentiation is sort of like a salad. Before you eat a salad, you want to toss it. Because if you don't toss the salad, all the heavy ingredients sink to the bottom. The things like the carrots and the celery and the tomatoes, they just sink to the bottom, leaving the lettuce floating on top because the lettuce is a lot less dense. It weighs less than the other ingredients. This is also true of the Earth. The less dense materials are the ones that differentiate it to the top. So this is a picture of hot molten magma. As you can see in this picture, it's very hot and it's still very molten, very almost liquidy. That's what you see in the red. And then this image is Earth's interior, and you can see those 3 layers, the core, the mantle, and the crust. Now the core and the mantle are also divided into inner and outer. The crust is